So welcome to lecture 1. So we are beginning with moving charges and magnetism. This is chapter 4 in our series. So we begin this with a very interesting experiment. Now this experiment is simply an observation of the scientist and teacher Hans Christian Ørsted. Now what exactly happened is, now Hans Christian Ørsted is a Danish physicist and chemist at Professor of Copenhagen. So what exactly happened is that the Ørsted was observing or trying to observe Ohm's law in his laboratory, and over there he observed that the compass needle suffers a deflection when placed near a current carrying wire. So this gave him the idea that there is some sort of a relation between the electric and magnetic phenomena, which is basically the starting point for the study of electricity and magnetism combined. Otherwise, before it, the two concepts were treated to be a separate entity. So if we begin further, so let us first of all discuss about the observation which a current carrying wire have on the magnetic field near it. So we are considering that there is a large cardboard. So we are considering that there is a large cardboard which is placed in a plane, and over here a small hole is drilled through which a current carrying wire is passing like this. We are connecting a positive terminal of a DC battery to this end, and from the lower end of the cardboard it is connected to the negative terminal, and a rheostat is attached over here, RH, EMF E. So this is how the arrangement is looking like. So as the wire is switched on, the current I is going to flow through this segment, and as current I flows through this particular segment, the iron fillings which is placed on this wire is started arranging themselves in loop like arrangement like this. So they started arranging themselves in a loop like arrangement like this. So there were concentric loops that were observed, and when the compass needle was placed, so the direction of compass needle pointed out that the direction of magnetic field is in this sense. So this red arrow is basically representing the direction of magnetic field as observed by the compass needle when placed at different positions on this cardboard. So the direction of a magnetic field can be determined using Maxwell's right hand rule. So we are first of all trying to understand that how we obtain the direction of a magnetic field due to a current carrying wire before studying other aspects associated with it. So over here we are saying that Maxwell's right hand rule So according to Maxwell's right hand rule, we will be using our right hand. So if we fix our thumb in the direction of current carrying wire, then our palm will give us the direction of magnetic field. So if this is my right hand, and if I am fixing my thumb in the direction of current carrying wire, then my palm will be pointing in a direction like this, that is into the plane of the board, and on the other side my palm will be pointing in the direction outside the plane of the board, something like this. So over here, this is the palm which is facing outward, and over there the palm is facing inward. So I say that the magnetic field on this side is directed inward, directed into the plane of paper, into the plane of paper, and on this side the magnetic field is coming outside the plane of paper. Magnetic field is coming outside the plane of paper, and that is the reason that if we consider a current carrying wire over a cardboard like this, so if I consider that there is a current carrying wire like this over a cardboard, so the magnetic field lines can be determined, or the direction of magnetic field lines can be determined using this Maxwell's right hand rule, where we say that the direction of magnetic field is in this direction. So if we place our right hand in the direction of current carrying wire, then our palm will point in the direction as shown on the cardboard. So I am repeating one more time. Place your right hand thumb in the direction of current carrying wire, and your palm will point in the direction of magnetic field. So this was the first set of things that came in, and now we will begin with the behavior of charge when placed in a magnetic field or when placed near a infinitely large current carrying wire. So let us understand this concept. So we are saying that a charge is projected near a current carrying wire. So we are considering something like this, that there is a infinitely large current carrying wire, something like this, carrying a current I, and a charge Q, which is a positive charge, is projected with a speed v in front of this current carrying wire. Now we know from the few facts which we have read till now that the magnetic field due to this will be directed into the plane of paper in this particular direction, or in this particular region where the charge is projected, and it was observed that the charge particle followed a path like this. So it followed a path like this. So this was the trajectory which is marked in blue for the charge particle when projected in front of an infinitely large current carrying wire. Now this new field which is exerting a force on the charge particle is regarded as magnetic field. Now a few interesting facts can be laid in over here. So now the first thing that we are learning is the value of force which this charge particle is experiencing. So I am writing the magnetic force experienced by the charge particle. So the value of force which the charge particle is going to experience can be written as F vector is equal to Q V cross B. So this is the value of force vector which the charge particle is going to experience when placed in a magnetic field. So from here I can say that F vector can be written as Q VB sin theta, and there is a directional aspect n cap associated with it. And if we only wish to write the magnitude of force, so the magnitude of force which the charge particle experience is equal to QVB sin theta, where theta is the angle between velocity and magnetic field. Now the first few things which must be kept in mind over here as per this formulation is, so the first notable fact which we write over here is, so the first one is that force vector is perpendicular to the velocity vector, and it is also perpendicular to the magnetic field vector. So since force is perpendicular to V vector and it is also perpendicular to magnetic field B vector, so from here I can say that F dot V is equal to 0, and similarly F dot B is also going to be 0 for the charge particle. So if we come to know that the charge particle is only under the influence of magnetic force and it is having a certain value of velocity and magnetic field, then F dot V and F dot B must be 0 for such a charge particle system. From this aspect, I can also say that F dot V is representing power. So power is also equal to 0 for the charge particle due to the magnetic field, and this power can be written as rate of doing work, that is dW by dt, and if I equate it to 0, so I say that work done by magnetic field is 0. So this is a very interesting concept, that work done by magnetic field is 0. Or I can say that since work done is equal to change in kinetic energy of the particle, so I can say that the change in kinetic energy is also 0, that is half m v square minus u square is equal to 0, that is v is equal to u. So from here I say that the another point which can be stated is that the value of speed, so speed of the particle moving in a magnetic field or under the influence of magnetic field only remains constant. So it remains constant. So speed of the particle moving in a magnetic field remains constant, although the direction can be altered, that is velocity can change. So velocity can change, but the speed of the particle moving in the magnetic field is going to remain unchanged. The next aspect which we discuss over here is the deflection of the charge particle depends upon the nature of charge. The deflection of the charge particle depends upon the nature of charge. So that is, if in the previous problem I would have taken a negatively charged particle, then it would have gone in the opposite direction in comparison to the positive charge. So if we go to the previous page, I can say that this positive charge is following a trajectory like this. If it would be a negative charge, then the particle would have followed a path like this. So the negative charge will be following a path like this. So the positive and negative charges do make a sense in case of the magnetic force which the particle experience. The next point which can be stated over here is the next point which we are stating over here is that this force is equal to qvb sine theta, and hence I can say that if v vector is parallel to b vector, or when theta is equal to 0 degree, then the charged particle will not experience any force. Will not experience any force. So if F is equal to qvb sine theta, then if the charged particle is projected parallel to the direction of magnetic field, then the charged particle will not experience any force due to the magnetic field. So these are some basic aspects which must be kept in mind while dealing with this force F is equal to qvb. Now we come to the nature of deflection. So the nature of deflection. The direction of the deflection of charged particle is determined by finding the direction of force or magnetic force, to be very specific. So if we consider that the magnetic field is present like this in space, that is, it is directed into the plane of paper, and we project a stream of charged particle from here which is moving with a velocity v like this. So over here, if I write it in this way, so in the vector sense I can say that the velocity of the particle over here is directed along j cap, v j cap, and the magnetic field is directed along minus b k cap. So if I find the direction of F equal to qvb, considering that q is positive, so for the q to be positive, the direction of force will come in the direction of v j cap cross minus b k cap. So over here, if we perform a cross product, that is j cross k, so it will give us the value I cap, and the value is calculated as minus qvb I cap. So the direction of this force is in the negative I cap direction. So if it is in the negative I cap direction, so the positive charge will deflect like this. So this is going to be the trajectory of the positive charge. And for the negative charge, if I place over here in this expression, if I replace q with a minus q naught charge, so the force on the negative charge Fn will become q naught Vb I cap, that is, the direction will be altered, so it will go in the positive direction, that is, the deflection of negative charge will be something like this. So the deflection is considering the positive charge, the deflection can simply be calculated or known by finding the direction of V cross B. So we can simply do it in this way, that we use our right hand, we take our right hand in the direction of velocity and curl it in the direction of magnetic field, and the thumb will give us the direction of V cross B. I am repeating one more time, just like finding the direction of the vector multiplied using cross product. So take your right hand in the direction of V vector and curl it in the direction of B vector, and you will get, your thumb will point in the direction of deflection. So to find the deflection quickly, we will be using that approach. So now we wish to understand the effect of reference frame, or basically the relation between the electric and magnetic field. So the effect of reference frame, or the relation between the electric and magnetic field. So let us consider this. So I am putting up the heading, reference frame and relation between electric field and magnetic field. So if we consider this, let us again perform the same experiment. That is, there is an infinitely large current carrying wire, and we now already know that due to this infinitely large current carrying wire, a magnetic field is produced in this direction, which is directed into the plane of paper B vector. So now I am fixing two reference frame over here. So the first reference frame will be the observer, which is standing on ground, and my second observer, so I am calling this observer as S, and my second observer is in this elevator. He is S1 and he is moving with a speed V in the upward direction. So we have the two observers as S and S1. So now I am projecting a charge particle Q with a speed V in this magnetic field, and the deflection like this is observed. So if we consider the value of forces which we have learnt and the things which we have learnt, so the force equation which we learnt over here was F vector is equal to Q V cross B. So now if we consider the two observers, so we are saying that there is no such electric field applied, but there is a magnetic field which will exert a force on the charge, and the charge is attracted towards the wire. So now if the observer S will report, then he will report that the charge particle was moving with a speed V, and there was a magnetic field present in space, as a result of which this F vector, which is equal to Q V cross B, acted on the charge and the deflection was produced. But if I talk about the another observer S1, so now according to observer S1, so according to observer S1, the relative speed of the charge particle is 0. So now the relative speed of charge particle is 0, and if the relative speed of charge particle is 0, then according to S1, there is no magnetic force acting on this charge because V itself is 0. But S1 will also observe the charge particle to be moving in the deflection direction as shown. It is because both S and S1 are not in the accelerated. So they are not an accelerating frame, that is, they both are unaccelerated with respect to each other, and hence they both will observe the deflection of the charge particle to be same. So now there is a fix. So we conclude that the electric field and the magnetic field are not basically independent of each other, So they both are the same entity which we called as electromagnetic field. So we call this as electromagnetic field. So the purpose of this particular experiment was to show you that while dealing with the electric effect or the magnetic effect, we cannot overlook the other. We cannot overlook the other. So if we are confined to a particular frame, we can treat that the electric field and the magnetic field as a separate entity, but they both are inseparable. They both are inseparable. So now we will be discussing about the motion of the charged particle in a uniform magnetic field. So we are dealing with motion of a charged particle in a uniform magnetic field. So we are considering that the magnetic field is present in space which is directed into the plane of screen, something like this. And the strength of magnetic field is B. The strength of magnetic field is B. It is directed into the plane of paper. Now we project a charged particle somewhere here into this magnetic field which is moving with a speed v. So now as a result of the force F equal to v cross b, the charged particle will start moving in a path like this and it will complete a circular path. So the charged particle will start moving in a circular path because of the constant deflection that is produced because of v cross b. If I find the direction of force, so at every instant of time, as we have already discussed, the speed of the charged particle under the influence of magnetic field will not change. So if we find the direction of force at each instant, so it will be directed towards the center F. So the force F is directed towards the center, which will be because of the magnetic force. And this magnetic force provides for the centripetal force, and hence I can write an equation like this, that the magnetic force is providing for the centripetal force, and I can frame an equation like this, that QVB is equal to mv square upon r. So the radius in which the charged particle is moving, r, is equal to mv by qb. So this is the formula for the radius of the charged particle in the magnetic field. Now since the speed is constant, so the speed is constant, so if we wish to calculate the time taken to complete the circle, so we are finding out time taken to complete the circle. So this time t can be calculated as the distance traveled, that is 2 pi r by speed v, and the equation is reduced into 2 pi m by qb. So this is the time period of the charged particle moving in the magnetic field only under the influence of magnetic field. So we see that the time period is independent of velocity or speed v. So if the particle moves faster, the radius is larger, but if they both originate at the same point, then they both will reach at the same point together. because it is independent of the speed. So if the identical charged particle, that is each having charge q and mass m, is projected into a magnetic field b, then they both will reach the same point together, although their radius may be different. So if we calculate the frequency of revolution, so this frequency of revolution is regarded as cyclotron frequency. So this frequency of revolution, which is represented as f or chi, which is equal to 1 by t, is regarded as cyclotron frequency, which is equal to qb by 2 pi m. This is regarded as cyclotron frequency.